So, yeah, Wednesday I'm going to go through like some Polymer rheology stuff that I haven't done, that I needed to do, but I haven't done yet. So, and then on Friday, so Friday I'll have the final ready, and I'll go through. It'll be like 2 papers, so I'll go through like 2 papers on Friday. So that's kind of what's going to happen this week, and then the final, like the last day of finals or something, but it's like a Thursday, I think. So that's when you can turn in the final. Or you can turn it in earlier, coming up, but basically, I think that's the last day you can turn something in. So, and then if anyone has like a problem with the grades or anything, I can like, I mean, you can do stuff later on to bring it up if you need to, whatever. Then like I can change a grade after the semester and up to a year after. So if anybody needs that. I think everyone's probably in pretty good shape, but yeah.
What's the difference in expectation between grad and undergrad? It's like the attendance.
What do you mean the final or after the semester ends?
After the semester, like you had mentioned at the beginning of the semester that this last homework was something for grads only.
Yeah, no, it's all right. If you're a senior graduating, then you don't need to do it. But if you're not graduating, you have to do it. But and if you're taking it for grad credit and you're a senior, no, it's doing a SEM thing, then you have to take it. So it's tricky. It's a complicated,
I think 2 year solo you wrote 80 for undergrad and genetic.
yeah. Yeah, so undergrads get a 1 grade boost, and I don't give like half days, so it's like either A or B. It's like 90, you're shooting for like an 80 if you're an undergrad. You get an 80, you skid it under the thing. So, and then if you're a grad, you're shooting for a 90, or maybe it's, I mean, I'll look at the grades at the end and kind of look at it. So, and if there's a problem after, again, like you can do fix things, whatever you need to do. And then change your grade later.
With your senior, they won't kind of throw your grade, the final.
You don't need to take the final. If you're, I mean, you can if you want, but you don't have to.
You know, if you don't take it.
Yeah, it doesn't matter. Right, yeah, it doesn't matter. Yeah, so you can, yeah, so some of you said you didn't need to take the homework this week, for instance, that's fine. Yeah. If it ends, if it ends up like it's messed up, just contact me and figure it out. There'll always be some pathway to get whatever you want, I think, more or less, It might be like do some more stuff or something like that, but anyway, but I don't think anyone's in that position for the undergrads, as far as I know. So Nickel isn't here. I mean, I think you probably remember. I didn't send a reminder. It's true. I'm gonna have it. Let's see. I have Nicholas Nichols. John Nichols.
Hello?
Hey, John, it's Craig. You intend to come to this class?
Yeah,
right outside the door. Oh, yeah, all right. I don't know. I thought he'd call you. Sorry if I said he's right outside the door. Yeah. Yeah, all right. Yeah, I told someone to go to 747. It's like, well, that's the wrong room. Pretty good, yeah. You get good weather. So.
To do some
That one's the right one.
regulations.
Yeah.
Oh, do I have to go onto this screen or?
No, you can do either. I mean, It would be better to get on this, but basically you can do that. Doesn't matter. But you have to, yeah. Or-
Just say, let's see,
It's actually, I'm running this on Zoom, so
call Zoom.
you could call Zoom, yeah, if you wanted to.
She sent me the link.
Let's see.
Is there a
Oh.
number?
Yeah, I can send it to you here.
Let's see what well, let me just log on to Zoom and see what I need, because if there's like an ID number here.
Oh,
Meeting
okay.
ID.
Yeah, yeah.
I can just punch in the meeting ID and join.
Right, yeah, right here. Meeting ID.
Yes.
I- 872-3367-9564. Oh, and the passcode is. Let's see, the passcode is like 1, I think.
There it is.
Right. So then I have to, let's see, let me get back here.
So make sure my audio is off. So
All right, so what do I, let's see. I have to allow sharing here. How do I?
let's see if I can. Hold on.
Recording in progress.
All right, so I'm muted, so I'll be catching on that, I suspect.
Yeah, but I don't see the other, how do I get the other window? I know how to do it on a Mac. Oh, wait, it's up there. It's like
So
up
you're in
there.
here. Oh, just maybe Max.
Yeah.
Just maximize. There's one window missing here. Closes that. Okay. Maybe that window? No. Oops. Why does Windows, let's see, where is the, it gets rid of this menu,
Yeah.
right? So why does it do that? Like, I need that other thing that was there before. I could never find
let's see
things in this, these Macs, so it's like a fish flopping on the
Yeah.
beach. That's good. Show,
I could just grab host for a second. That is.
okay, that'll work, maybe. It's an odd way to do it, but
Yeah, we'll figure it out. There we go. Just close this down now.
here, you do it.
Yeah.
I'm not touching anything. I've run into a lot of problems this semester with like weird things happening, like reverse type.
Sort of specific systems. Hold on, let's get rid of these windows here. All right. Yeah, so let's go back to the beginning. So can I start by asking, have we covered X-rays in here and neutrons at all?
Yeah.
So for statics, scattering them?
And the in-plane scattering and one XPCS.
XPCS, okay. So we're comfortable maybe with the concept of the scattering equation.
Determining the tube diameter with, dynamic heat.
So we have done some.
Just
inelastic.
mentioned, yeah.
All right, well, we'll go a little bit down the rabbit hole. So just starting off with the concept of elastic versus inelastic scattering. So anybody know what I'm talking about when I say elastic versus inelastic scattering? Okay, so elastic scattering is structure. It means there's no change in the momentum of the scattered particle. So your neutron comes in, it interacts with the sample, and it scatters off of one of those nuclei, and it changes its direction. And the difference in the direction of the incident wave vector and the outgoing wave vector gives you some scattering angle. It defines some scattering wave vector Q that can be related to each other. And this is how we figure out the structure of molecules in a scattering experiment, is by measuring the intensity as a function of this scattering angle. Now that's fantastic, tells us a lot of information, but what we can also do when this incident particle has mass is follow the change in velocity of that scattered particle, which would translate then to a change in momentum. Due to momentum conservation, that would mean that we're gaining or losing momentum in the collision itself. And that should tell us about the motions of the atoms in the sample that we're scattering from. Okay, so if we know the wavelength of the incoming neutron, we can calculate from that we know the wavelength, we can calculate from that a velocity. We then have our sample to detector position. We can calculate the expected arrival time. And if that arrival time is on schedule, it's an elastic collision. And if the arrival time is slow or fast, we have gained or lost energy in the collision itself. Okay, and that's how we are going to be looking at inelastic scattering. That's the idea. And that inelastic scattering is measured as a function of change in momentum, and it's measured as a function of change in scattering wave vectors. So we have both a length scale dependence and a time dependence in the collision. All right. So the goofy stuff that you're seeing down here, when I think of neutron scattering, I think of sort of a quadrant of you have elastic, and you have inelastic, you have coherent, and you have incoherent scattering. And so neutrons are different from X-rays or light in that you have both elastic or you have incoherent and coherent scattering involved. Coherent scattering means scattering from a pair. So you have a plane wave, you know, your Bragg approximation, you have a plane wave interacting with a set of atoms, and you're seeing essentially the constructive interference patterns from that wave interaction. And you see information about pairs in space. Yeah. In incoherent scattering, you're seeing information about a single atom. And that leads to some very interesting math that I'm not going to try to repeat here, but it basically goes to reflecting this difference in the dependence on the scattering, on the neutron scattering length of a particular set of atoms, where this is reflecting the position of one atom in space as a function of time. So as it moves as a function of time, think about you get a signal if I'm standing in one place, and that's just incoherent scattering. If I move away from that place as a function of time, and then I measure the intensity as a function of time, that intensity will drop. And that tells me how long it takes to diffuse a certain distance. So if I measure that intensity as a function of momentum transfer or time at different length scales, I will see that this full width half max here varies as a function of Q. And you'll see this following some dependence there, right? And that dependence is highly correlated, not highly correlated. If you have a diffusional dynamic going on in, say, a liquid, so suppose you're seeing scattering from a polymer or a very small molecule in water, what you might see is that you have something looking like the time, the relaxation time, or the the full width at half max. You can do it in energy or in time. So this would be a function of energy, but that this would be proportional to 1 over the length scale squared, or Q squared, where Q is scattering wave vector, or 1 over length scale. All right. And that diffusion, that time would then be related to the diffusion coefficient. Yeah. So if you see a nice quadratic dependence, then you might have a diffusional dynamic. Now, coherent scattering is different. Coherent scattering means you're following the lifetime of a pair. So how long does a pair of atoms stay at a certain distance? That's what that would be telling you. So this is something like I have a lipid membrane and it's fluctuating, and I pick any 2 points defined by the scattering wave vector Q along that membrane or in a polymer chain, let's say, and I ask how long does that correlation persist as the molecule moves? So if you have some chain fluctuation that moves that correlation out of the appropriate length scale by bending, I would see my signal drop. And that tells me the lifetime of a pair correlation. Okay. Now, what you're seeing here is a convolution of 2 different signals. And this is the benefits and the penalties of using neutron scattering, is that you simultaneously are seeing both processes. But it's a function of this variable B that we're talking about.
The single point is no, but you have binary interference, right? And then with the incoherent, there's no binary.
There's no binary interference. So what you're seeing,
Atoms kind of just roll, as a nuclei rolling.
yeah, this is the incoherent background.
I mean, I always just subtract it, throw it away.
Exactly. So for structure,
I don't
if you're-
know exactly where, I don't know anything about it. I always say it's like top ten.
so it's not Compton. Compton is photon scatter, neutron scattering off of 3 electrons, right? So it is, oh, I'm not going to try to explain that.
That's all right. Clarify it for me.
Yeah. So really, when you're looking at the difference, so for coherent scattering, you're always looking at the difference in the atomic scattering length density, where B, so we'll call this the atomic scattering length density, and what you're seeing, that's terrible. What you're seeing in that is the sum over all atoms. So in your sample,
Dependence if it doesn't have to do with structure. But incoherent. It doesn't have a Q.
it does if there's dynamics. So in the energy transfer, it has a strong Q dependence. In integrated energy, it does not. So if you're doing a structural measurement, so in a structural measurement, oftentimes the spectrometers are set up so as they have no time resolution in their signal. So you say we should have started with reactors versus spallation sources. So if you're doing a small angle neutron measurement, let's say, you're simply taking a stream of neutrons coming off the reactor, scattering it off the sample, and waiting over here with the detector and counting neutrons hitting you as a function of position, integrating, and taking that value. Now, if there's a change in energy transfer, right? If there's an energy transfer in the collision, you still see all of that integrated together. Now, if I have time resolution in my detection, so say I'm sending pulses of neutrons at you, scatters off the sample, and I don't see, let's just make a new slide here. So if I put into the detector or into the signal, I put in pulses of neutrons, okay? So pulses. And these hit the sample and scatter. And they scatter on our detector in some pattern. But if I look at these in time, if those pulses are actually turning into broadened patterns, then I know that I've had an energy transfer. Yeah. And if I look at that as a function of energy transfer in Q, what you would see for the incoherent scattering is you would see some dependence here as you go to higher and higher Qs. This would broaden, assuming you have some diffusional motion, and the full width at half max would broaden. But the integral of these, if you integrated all of these in the same chart, it would be a constant. If this was the incoherent scattering, right? That integrated quantity is a constant. But the shape of it will distribute wider and wider and wider as you have energy transfers over shorter distances, right? Over shorter distances, it is more probable that your particle has left that volume. So I'm asking the question, in an incoherent scattering experiment, has my molecule, let's say a hydrogen atom, has it left a radius R1, R2, R3, where this is then related to the scattering wave vector Q, as Q is roughly proportional to 1 over R. And what you would see is that the probability of it staying there as a function of time goes down. But the integral is the same. You always have the atom there at the beginning, and it always leaves. But the time it takes to leave that those volumes will change. So longer scattering wave vectors, slower probability or slower time to leave that volume. Higher scattering wave vector, it leaves much more quickly. It gets out of it. Okay. This is what it does. So that's hopefully answers the question. Kind of.
Because the Q is defined in terms of a binary interference.
Well,
So it's kind of hard to say. Anyway, go ahead.
well, it's not a binary interference, right? So scattering wave vector,
It isn't really.
it can be related to that in the case of coherent scattering, but in and of itself,
Okay, right, not
it's
really-
just a vector, right?
Right.
So it can be defined as a point vector as well. So sorry, I'm trying to show you here.
Yeah.
This is real data where you're seeing water as a function of scattering wave vector has a sort of broadening effect here. And then when you measure that, you can see this broadening. Okay. So concepts we also should have covered. So let's just quickly add one more slide here while we're at it. So time structure in the neutron source. Because of what we're trying to do in measuring changes in velocity, what you need to do is introduce time structure in your source. So you're not just shining a light on the sample with a laser. You're not just opening up the synchrotron and bombing it with X-rays. We need a pulse structure or some kind of a time encoding for the arrival of the neutron from the source to the target. We need to know the velocity of that neutron and how long we expect it to take to get to the sample. And so there's a number of different ways that we have to do this. Sort of the old-fashioned way is to use monochromatization using either some kind of a analyzer crystal or a chopper system. And so this is what leads to techniques like triple axis or time of flight spectroscopy. More,
Like, so neutrons have mass,
yeah,
right? So they compare the X-rays with dollars. So that they have, so anyway. In
yeah,
other words, it matters like when the time of detection goes with energy. Basically.
exactly. So your incident neutrons need to have,
If you have like a track that spins around, you get this one velocity coming out, which is an energy. That's what a monochromator is.
Yeah.
I've got a helical tube that spins pretty fast. It can only allow one speed of neutrons flying through it.
Yeah.
Because their particles not.
yeah, I should have put this. They're very cool. They're like a little screw, right?
Yeah.
And so they turn at a certain velocity, and only if you're going the exact correct velocity that the screw sort of goes in line with you, you pass through that, and you select for one velocity.
So that's a monochromator for neutrons. It wouldn't work with X-rays.
No, it wouldn't, I mean, unless you had something relativistic, right?
Right.
So it doesn't work for X-rays, but if you have a particle that's moving at a couple thousand meters per second, it's very reasonable to construct such a device. The other way to do that is
It
to,
has to be big too. So X-rays can be small devices. These have to be human size.
oh yeah, yeah, so.
And the distance of the thing is gonna be.
Yeah, I mean, it's probably what, a neutron monochromator, probably the size of a desk.
Yeah, so they're big ones.
Yeah, there's a big spinning thing covered in cadmium or some boron containing alloy.
Magnitude and size between X-ray.
And maybe 7 to 10 to 15 orders less in flux. But this is sort of the old-fashioned way of taking a nuclear reactor, right? So how do you make neutrons? You have a nuclear reactor, and in that reactor you have some fuel elements, and they're generating neutrons all the time. You add to that some kind of a thermal moderator to bring the temperature of the neutrons to the appropriate temperature. That defines their velocity. And then you bring that out into some guide, and that guide will then go into a monochromator. And out of that comes neutrons at some particular wavelength. So wavelength of neutrons for use in soft matter studies would be something on the order of 6 to 15 angstroms for a structural measurement. Well, for a small angle measurement, it's the instruments I know, you'd be somewhere on the order of 1 to 15 angstroms neutrons. Now, if you're doing inelastic scattering, you tend to use sort of the low end of that. But that's fine. So this gives you a continuous stream of neutrons at a specific angle. Now, more recent developments use a linear accelerator to generate protons. Those protons hit some kind of a target, mercury or tungsten, and from that collision, you will generate neutrons through spallation. So spallation, just those, the heavy metals just disintegrate the nuclei, and from that disintegration, you will get a number of neutrons. You can then take that collision into some kind of a moderator, and out of that, you will receive a pulse source of neutrons operating at the frequency of the linear accelerator. So you can generate these protons at 60 hertz, let's say, and that means that you'll get neutrons coming to your instruments at 60 hertz.
So the linear accelerator is 1 mile long, and the building, the target. So basically, this is a big time up. So it's $500 million to build that machine.
Yeah, and that was 20 years ago, it was $500 million. Today, it would be several billion. Yeah.
Nuclear reactor's got a bad name. I think that's
For sure,
really
for
what it
sure.
is, you know? If anyone had the choice, most people would choose the reactor.
So we will disagree about this.
Yeah.
Um,
No one would ever build a $1 billion machine.
So everybody is now building linear accelerator-based
Because
solutions.
they can reactors, that's why.
No, so the difference with these things is
For
what?
good reason.
A nuclear reactor is a nuclear reactor, right? It means you have fuel, you have a reactor operating. It has a lot of benefits in its reliability,
It leaks tritium.
or it produces tritium, depending on your, yeah. So there's a lot of contamination and all sorts of stuff. But the beauty of a spallation source is if I turn the electricity to the accelerator off, my neutrons radiation stops, right? You don't get a lot of gamma, you don't get a lot of the other kinds of, you don't have radiation coming from the decay of plutonium or of uranium in the fuel. What you have is neutrons and a small amount, relatively small amount of gamma coming off of the spallation reaction. And so that means that your only sort of contaminations radiologically are from activation, right? So neutron activation. So essentially neutrons can be absorbed into a nucleus that creates an unstable nucleus which decays. That's radioactive, but you don't in and of itself have radioactive material at the site. So there's sort of a safety factor with these. The other thing, as an inelastic scattering person primarily, I think we benefit enormously from the time structure. But having said that, you could do all of these experiments on a reactor source as well. You pay a price in terms of throwing away flux. So spallation sources in general tend to have pulsed neutrons at very high brightness. Reactor sources have constant neutron flux at relatively lower brightness. So the integration is comparable.
Stable.
Yeah, no, the stability of a reactor is also something not to be dismissed, because spallation sources, as they are developed, the stability of the linear accelerator and the stability of the target are legitimate concerns. So when I started working at the national lab using a spallation-based source, it was about a quarter of the power the brightness it operates at today, but it was also operating maybe 70% of the time it was supposed to be, just due to various failures inside. And today, it operates about 95% efficiency. 95% of the time it's supposed to be operating. But the point being that this time structure in your intensity of the incoming neutrons is built in, okay, to the spallation source. And so that's very helpful when then you go to try to clock your neutrons. So what this leads us to is the point that there is sort of a super diagram here of what kind of dynamics you'd want to study in time, and the associated energy of the scattering phenomena, and then a length scale embedded through the scattering wave vector in your measurement. So if you want to understand, let's say, polymer dynamics, rotation, or dynamics of macromolecules, so overall diffusion of, say, a polymer chain, just fluctuating in water, you might look at a technique called neutron spin echo or X-ray PCS. If you want to look at smaller motions, like, let's say, motion of a small molecule diffusing through a polymer matrix, which is an example I'll show you, then you might look at a technique called neutron backscattering, which is looking at motions on the order of nanoseconds to tens of picoseconds. Whereas spin echo is looking at motions happening, almost up to a microsecond down to picoseconds. Faster dynamics, still, you can use methods like time of flight, where you're literally just timing the collisions. And that's for very fast dynamics, like molecular vibrations. Very helpful for magnetic systems. So the point here is that you have to make a trade-off in terms of length scales you're measuring and time scales you're measuring, because you're getting both of those in the way you analyze the data, the way you conduct the experiment. And that means that you have to develop different types of spectrometers for different ranges of dynamics that you want to study. So it's not a one-size-fits-all, I throw everything in my Raman or my DLS and measure diffusion. In neutrons, it's a little more involved because you're seeing multiple levels of dynamics depending on which level of scattering you're doing, which sort of range that you're in. All right. Does that make sense? Anything yet? Does anything make sense?
Well, there's a lot of axes on this thing.
Mm-hmm. Okay, yeah. So energy.
I always tell my grad students to first say what the axes are. on their
That's
plot.
fair, that's fair. So in the actual scattering experiment, what you're going to be seeing is scattering wave vector. So typically in a structural measurement, right? What are you measuring? You're measuring intensity versus Q, right? And you have some structure and you're fitting that structure to describe the polymer mesh or something, okay? In an inelastic experiment, you're measuring, like I was showing you before, you're measuring the energy, so the change in energy from the collision, you're measuring the intensity as a function of time and Q. So Q would be some perpendicular vector going back, and then you can have a gain or a loss in energy at every Q you measure. And so that means that your wave vector Q is related to the length scale you're measuring or probing, and the change in energy of the collision here is related to time through Planck's constant. Okay, so what you're really seeing, the data I'm going to show you will typically
equals H nu.
Yeah, E equals H time.
Nu is 1 over time.
Exactly. So frequency is what you're actually going to be seeing most of the time. So you'll see, I think it's most convenient to show this as frequency. And then I tend to transform the intensity itself into something called the dynamic susceptibility. I won't do that for all of these, but one of them I did for particular reasons of combination with other methods. So the other thing is to recognize that, inside this experimental space, there are many techniques overlapping. but there's sort of a unique role for neutrons in the middle there. Neutrons are really good at probing dynamics on the order of tens of picoseconds out to hundreds of nanoseconds. At length scales of hundreds of nanometers down to, angstroms. And so that's a kind of a unique space there where neutrons are really, to me, the only game in town. So inelastic X-ray scattering is getting better, but it is extremely destructive to the samples, whereas neutrons are not. Neutrons don't tend to damage the samples that you're measuring, right? So you can put a whole bacterial cell in a neutron beam, leave it there for 4 hours, and it's still alive. It's gonna die, but it's not yet dead. Whereas if you put, a piece of polymer into an X-ray PCS experiment, that polymer is destroyed in a fraction of a second.
So then, it was looking at curing of epoxies and they put in kind of a tracer particle and see the motion of the particle to get kind of the viscosity of the,
In light or in X-ray?
using XPCS.
Yeah. Well,
So that's up at the top or?
it'd be down here. X-ray PCS is down here.
Oh, I see.
So
Alright.
X-ray PCS is, it overlaps the time scale of spin echo quite a bit. And the scattering wave vectors as well, but it's so damaging because the intensity of the X-rays destroys the sample. So by the time you are measuring, microseconds, that sample is degrading and destroying itself because the intensity, the energy being transferred in there is so high. Whereas the neutron energies being transferred are very low. So if you're using cold neutrons or thermal neutrons, they're just not that damaging.
And you mentioned you had to do different
You have to be
exposures.
panning
to
it
find
and
the-
exposures
to
and,
find the exposure time.
Yeah. So it's a thing, and especially something like an epoxy that's gonna be reacting as well as you go, probably as a
Yeah.
function of the energy provided, so.
Right.
It's a technique that I don't. We've had conferences about this and the neutron people think we win. But
It's
the
also
neutrons
roughly
are-
10 times more expensive.
Yeah.
right?
Yeah,
I mean, actually, you go from DLS, and then times 10 is XPCS, and times 10 gets you a neutron.
probably.
It'll just
Probably.
hit you into the door, maybe another 5 times what you think.
Yeah, that's
actual
probably
energy
true.
machine.
That's probably true. So, I
Well,
mean,
what's money,
if it's worth doing, it's worth doing.
Well, also like who funds it, so it's kind of like DOE's the top dollar, like when they want to do the Human Genome Project, it was too expensive for NIH. So DOE did, it, like, so this is like,
Yeah.
because they do nuclear bombs.
Yeah,
Like they know how to spend a ton of money really fast. So basically, all the neutron stuff is gonna be DOE.
Well,
Some
Department of
X-rays,
Commerce.
some
Department of
X-rays,
Commerce,
some of the
that'd be
X-rays like NSF funds.
Yeah.
Like,
yeah,
And the DLS is like your backyard.
you can buy it. There's several here in the building, yeah.
Yeah, that's not. It's just kind of funny how the orders in this thing are important too.
That's true, that's true. And so the accessibility to neutrons is not very open. That's the other one. And yeah, it costs 30 grand a day to rent beam time on a neutron beam line. That, costs $20 million to build. Whereas an X-ray beam line will maybe cost you $3 million or something, all said and done.
I'm gonna try to ask this right.
Yeah.
So the X-ray, you get more of a time scale than the X-ray, with, like, since it doesn't destroy the sample, what insight does that give you, like, in terms of like the dynamics?
So this is what I would be calling slow dynamics. So here you're talking about things like, you might be talking about membrane and the fluctuations of the membrane. You might be talking about the polymer chain dynamics. So as the polymer backbone chain, what is the frequency of its relaxation time? And if you're measuring that as a function of temperatures, let's say, you might want to follow that for some kind of processing or rheological property. What else?
I mean, you can deuterate.
Yeah,
Anything
yeah,
with
that's the other-
hydrogen in it, so
yeah.
any hydrocarbon, this is gonna be the best. technique.
That's what we should have covered in the
So
last slide,
basically,
yeah.
If you take a micelle that's got sodium ion from the outside of it, the one like shampoo, when you stick it in an X-ray beam, the only thing you see is sodium. All the soft matter, all the hydrocarbons are invisible. So the neutrons, you can hunt.
Experiments of this, but butadiene is one of them where they did a lot of coherent scattering. Side chains versus main chain, you can, tune out the main chain solvent and then follow the side chain dynamics. Then you can do the reverse where you follow the main chain dynamics independent of the side chain dynamics. And then what you would see is you follow the relaxation time and you might see the main chain as a function of Q. The main chain might be much slower than, say, the side chain dynamics. And you can sort of extract from that a hierarchy of time of energy lengths, energy scales, and in the relaxation process. So this is a unique capability of neutrons to tune that around. Okay. So things I wanted to cover. Just there are different kinds of neutron spectrometers. So you have triple axis techniques. So triple axis is where you tend to use a monochromator or an analyzer, excuse me. So you can, the other way, instead of using a spinning monochromator, you can find a crystal that only reflects one wavelength of neutrons. So in this sort of white, imagine white beam light coming in, it hits this crystal. Off of that crystal scatters only one wavelength of neutrons. So it has one velocity. Now I will have that interact with my sample in this position. Right here, sample, and then I can swing this apparatus around. At the end of that, I will then have another analyzer crystal. I'll have the same analyzer crystal. So if the neutrons that are coming in have changed velocity, they will be rejected. And what I will see is a drop in intensity from my initial time. So if this is my incident intensity, and then it interacts with the sample, I'll see a different intensity of the interaction, because this will be rejecting everything that isn't the same wavelength that then goes into the detector. Okay, so this is the first type of inelastic neutron scattering measurement that got Brockhaus. So it was Brockhaus? Yeah, got the prize, Nobel Prize for this. So figuring this out. Now this is measuring one scattering wave vector at a time with one angle of your analyzer crystal, which gives you one energy transfer at a time, right? So you're measuring very slowly across that three-dimensional time, length, scale, intensity space. You're measuring a single point at a time. What you really want to be doing is measuring all the scattering wave vectors simultaneously and all of the times simultaneously. So a spectroscopic technique rather than a one-off measurement over and over and over again. And so what you have with that, the next sort of generation of this was the so-called time of flight spectrometers. And in this, what you're doing is you're using a series of choppers typically to phase the neutron pulses or phase the incoming neutrons. So you physically block the incoming neutrons unless they're coming in at a certain velocity. They'll pass through all of these choppers if they're going the exact correct velocity. So you get this narrow beam of neutrons arriving at a specific time that you measured that time, and then you know how long it should take to get to the detector if it's in an inelastic collision, right? Or an elastic collision, no energy transfer. So that anything getting there too soon or too late has an energy transfer, and you will tune the incident energy. So the sort of the time it takes to get from the source to the sample and the sample to the detector, that's all subject to the time scales involved in actually electronically measuring these arrival times of the neutron, right? So I need to be able to electronically distinguish the arrival times on the order of microseconds, nanoseconds. Yeah.
Is the chopper like a fan kind of?
It's exactly like it's a big hunk of metal with little holes in it.
Okay.
Yeah. Spinning at thousands of RPM. It's like a car engine with just a big bump. And they're all phased together exactly in the right time. Yeah,
They're kind of big, right?
they're big. They're Yeah, I mean, they're yay big. Yeah. And they're usually embedded in these gigantic concrete blocks. It's quite a thing.
I mean, there's gonna be a lot of radiations coming out of these things.
Yeah, yeah, absolutely.
And they themselves will become radioactive over time.
They do, right? So you're usually, the neutron beams are, say, yay big. And so the gap in those will be relatively small, but then there's a ring in that metal that is being irradiated. And it's usually covered, in some neutron absorber. So it's sitting there just accumulating dose over time.
If you like to do crazy things, it's a pretty good fuel to get. Anything goes.
Yeah, well, yeah. So this is still an active design, and the point of these time of flight instruments is that you can vary these distances. So the source to sample distance, the sample to detector distance,
I mean,
the angles.
Size of like basically a big.
Yeah.
Almost a building.
Yeah, the detector for CNCS, let's say, is like this big.
Yeah.
Right, it's like the end of this room, basically.
Yeah.
And it's all coated in, helium-3 fine wire detectors. And so they're very expensive giant detector banks. And there's 4 of these type of instruments at Oak Ridge, for slightly different pieces of this. So what we're talking about, this is this kind of techniques. And so there's lots of little specialty pieces inside here, right? Different spectrometers that cover different little parts of that. Okay. Now, this is if the neutrons are moving relatively fast. Okay, so that the energy transfers are large. There are big differences in the velocity as a function of the scattering. That corresponds to fast dynamics. If you want to start looking at slower dynamics, what do you need to do? You need to make the time of this neutron going from the sample to the detector, you need to slow that down as much as possible in order to allow 2 neutrons with different velocities to travel different distances in time. Right? That's how we're getting the difference in arrival time. And so another way to do this is to build the so-called backscattering technique. So you're looking here at essentially extending the time it takes to get the measurement. So what you'd be doing is you bring in your neutrons, it hits your sample, it bounces off an analyzer. Well, so in this one, this is a reactor source backscattering experiment where you're using a Doppler to analyzer crystal. So this is a very old-fashioned way of generating a monochromatic beam in a backscattering experiment. But it's ultimately what you're going to do is bounce off of an analyzer crystal to block in a single wavelength coming back to the detector and measure your time that way. So only neutrons that come in with a particular wavelength will backscatter off of that detector and go to the detector, or bounce off this analyzer, excuse me, and come back to the detectors here. Okay, so what you're doing is doubling the path length from the sample to the detector. And that allows you to have more time for them to sort of distinguish themselves from each other based on velocity. In a spallation source, you don't need any of this mess. You just bring the neutrons in using choppers. Okay. And for really slow dynamics, you can't do that, right? Neutrons, essentially, when they get really slow, you can't distinguish the changes in the scattered velocity or the velocity of the scattered particle. So what you'll do is you'll use the neutron's spin to encode its velocity in a magnetic field. So what you do is you polarize the neutrons coming in, you allow them to process through a magnetic field. You then, on the other side, would have them process through an opposite magnetic field so that their spins should echo back at the same distance on the other side and be able to pass through an analyzer to go to the detector. If the sample scatters inelastically that neutron, the velocity will change and it will no longer spend the same amount of time on the decoding side of the spectrometer, and it will therefore not echo back into polarization and it will be rejected. And so you will measure this as a drop in scattered intensity, knowing that your sample has done this. And by altering the magnetic field strength, you can relate that time And you essentially can construct something like an intensity over intensity of a sort of no magnetic field. And you can see in this case, a different kind of scattering experiment where you're measuring really a decay time. So this is almost, neutron spin echo is a lot like DLS, where you're measuring a drop in intensity as a function of delay. Okay, and this is very, useful technique for protein dynamics, polymer dynamics, lipid dynamics, things like that.
Kind of parallel to the NMR, right? So, I mean, now NMR is using magnets,
Yeah, so
big magnets.
this is basically two NMRs stuck sort of butt end to each other, right?
This kind of spin precession thing.
It's exactly
all
what
the
NMR is.
nomenclature came from
Yeah,
NMR, I think, originally.
so a
It's
new,
almost like press polar light scattering too. Kind of looking at.
it's a pump probe technique, right? So it's
Yeah.
like NMR, spin echo NMR is you polarize your atoms, and normally when they decay back, they emit that radio frequency, and you measure this. And if you have a sequence of pulses, what you can do is catch the resonances as they come back, right? So they should echo back as sort of a function of time. If you polarize and then polarize again, you should be able to see an echo of that polarization at sort of two frequencies. This is really, it's like putting two NMRs back to back. So you're polarizing, you're letting it scatter, and then you're repolarizing on the back end. And if it spends the same amount of time in both fields, you see the echo. And if it doesn't, you don't, and it's a drop in intensity. So essentially you'd see, some drop in intensity, you'd find T1/2. And just like a DLS experiment, that's the measurement you get.
So we can do that measurement, NMR measurement, that you see it.
Some of them, yeah, some of them, but their timescales are not the same, right? So NMR timescales, the electronics of generating those pulses in the NMR are not, you cannot get as fast as a neutron spectrometer. You're still in microseconds. And in fact, that's kind of the example I wanted to show here. We were looking at the dynamics of molecules moving through Nafion polymers. So I can sort of skip to the end. I don't know how much time we have left.
We have 5 minutes.
Yeah, so we'll go quickly through
Nafion
these.
is like- Maybe you guys know it's like a membrane material.
Yeah, so Nafion is essentially a proton transfer membrane, right? So you're using it in fuel cells, things like that. And what happens when you react hydrogen and oxygen in this is that you generate water or you generate other solvents. So here we were looking at this as a function of adding acetone to these systems as some kind of a detection measurement. And what you can see here is that we were taking neutron measurements to measure diffusion over very short distances. And we were using NMR to measure diffusion over much longer distances. So NMR tends to measure dynamics on the order of microseconds and higher. And if it's a diffusional process, that should be connected to motions occurring over microns in length. So what you'd see from an NMR experiment here is that you have essentially domains in this polymer, right? So in this polymer, what happens is it has some interesting functionalities where these fluorocarbon or these acid regions, these sulfonic acid regions, will form hydrophilic domains. So water and other solvents will accumulate in these domains. And the transport within these systems is important because as you generate these domains, the electron transfer properties eventually degrade, right? And so if your goal is to look at the transport of some other solvent through this material as a detection, then we need to measure this using whatever techniques we have. And so over long length scales, again, you can measure using NMR. So we can measure diffusion coefficients over these length scales. But if you want to use shorter length scales on the order of nanometers, you need neutrons. And so what we're seeing here is that over very short length scales, the diffusion is much faster than once you start trying to bridge between domains inside this polymer. And so the morphology of the polymer that develops can introduce a hierarchy of dynamical processes where you have molecules moving very quickly inside one domain of the system, and then they reach a barrier. And the transition across that barrier is probably what you're measuring macroscopically. You're measuring the slowest step macroscopically. And so what we can do here is understand which of these steps is the most relevant by measuring it over different length scales. So we would ask the question, how long does it take my proton in the acetone, let's say, to move over 1 nanometer? How long does it take for that proton to move over a micron? And then by looking at that as a function of different times, or a function of different length scales, we can see significant differences. So free acetone would be diffusing, at something like 4 times 10 to the 9th meters squared per second in the normal free diffusional measurement. Whereas if it's diffusing through the polymer, we see significant decreases at the length scale of that domain. It also just simply diffuses less inside the polymer. So an interesting way to see the hierarchy of dynamical processes. Sorry, was there a question?
Yeah, does the neutron beam itself, I think we went over like attenuation for beams. Does it attenuate the same way as like 5 years whenever it's all?
It-
You have to take that.
So it attenuates, I think, does go by Beer-Lambert. But there's an absorption factor and then there's a scattering length. And a scattering cross section. And so when you produce a sample for a neutron beam, you're aiming for something greater than 90% transmission. So essentially you have to thin the sample to the appropriate thickness. Conscious that you don't want to see multiple scattering events.
The big difference is that it absorbs by accumulating neutrons in the
Inside.
material, which changes the mass of the nucleus, which makes the material radioactive. So
Yeah.
anytime you absorb neutrons, you're kind of making a radioactive product.
Yeah.
Of some kind. It could have a short half-life, it could disappear by some kind of decay. But generally, it's not a good thing. Like if you stick your gold ring into the beam,
Yeah, you're not getting
your
that back.
ring will get
Yeah.
from the you'll have a radioactive gold ring.
Yeah, but so from an inelastic scattering standpoint, the thing that really ruins your experiment is multiple scattering events. Because it's very hard to model something that scatters off of 2 atoms inside the system. So if it has 1 scatter, 2 scatter, how the heck do I put that picture back together in a momentum balance? It's very, very difficult to do. And so you need to keep the samples thin enough that the probability of that event is very low. But it's not the same way as an X-ray. It's like chemically degrading the system. Neutrons, yes, will decay the sample, but the collision, the flux is just so much. You're just 10 orders, 20 orders of magnitude less flux, maybe not 20, but like 10 to 12 orders of magnitude less
With
flux.
modern synchrotron,
Yeah,
maybe
it's-
hundreds,
yeah.
maybe 1,000 plus some cases.
Oh, yeah, I mean,
Yeah,
millions of times less
Right.
and lower in flux.
yeah.
Tens, hundreds of millions of times lower, yeah.
Well, lab X-ray source is much more powerful than the.
Than the best neutron source in the world,
Yeah.
yeah.
Anyway, so we're out of time.
Yeah.
Thanks for, so we should. Questions,
Yeah.
you can.
I'm around.
Don't answer it.
Thank you.
Yeah. I was playing with this. I don't know if you remember mods. You stick me up. Just playing that. Yeah. Oh, so like I was looking at the. So I know like I think we're seeing is sort of an interesting. You do the bits, right? You do the bits, you get 2 length scales out. And you see these 2 length scales. It gives us 3D and 2D scatter. Mesh size and 3D, the mesh size and 2D. Let's come back together. So what I'm trying to do is put back together. Sort of geoelasticity, the persistence length, related to the length scale. of either dimension. So I think that's what's going to end up being here. But I was just going to show this because it all comes together nicely with the dynamics actually. So,
Yeah, sorry for my interruption.
oh no, it's
I
fine.
think that they don't.
Yeah, that's true. I don't know.
Yeah.
Yes, so I've been trying to
Here's
dig
the,
through.
tendon sheet.
Oh, thanks. All right. Yeah, thanks. I forgot about that.
I've been trying to